Hello and thank you everyone for attending today's webinar, Actuator Selection 101, Best Practices Engineering Roundtable, brought to you by Design World Magazine and Bishop Weiscarver. We'd like to thank our presenter, Brian Burke, for being here today. I'm Mike Santora, Associate Editor for Design World Magazine, and I'll be your moderator. Brian Burke, Senior Product Manager at Bishop Weiscarver Group, is passionate about product development and manufacturing with educational backgrounds in computer-aided drafting and design and manufacturing technology. He has more than 13 years of experience in the automation industry with extensive knowledge from the production floor operations to product marketing activities, including CNC machining, lean manufacturing, equipment acquisition and implementation, product literature and catalog development, and trade show expositions. So, without further ado, here's Brian Burke.
Thank you for the great introduction, Mike, and a special thank you to Design World for hosting and promoting this webinar. We have an exciting topic today, and you can see the agenda. We're going to be talking about Actuator Selection 101 as an introductory best practices and an engineering roundtable towards the end. For those of you who aren't familiar with Bishop Weiscarver Group, we're going to start off with a brief company overview, look at some of the range of the products that we provide before jumping into the webinar topic. We're going to look at terminology and jargon that we use in our industry to explain these products. And then we're going to look at all the different component types, the advantages and disadvantages of each. Then we'll look at the factors that you should consider during selection. Following it up at the end with an engineering roundtable with our application engineering department of experts. We're going to discuss the best practices and other advice that they have for these processes. Bishop Weiscarver Group is a women-owned family of WeBank certified companies that works with manufacturers to engineer and design linear and rotary motion solutions. We also do custom complex assemblies, and we can do programming, control systems, and optimal embedded intelligence systems. Together, we've been in business over 65 years and have served 20,000 unique clients. We continue to be a single point of service, providing custom designs, increased efficiencies, and accelerated time to market. We manufacture and distribute a wide range of motion products, including components, linear guides, telescopic slides, and complete automation solutions like actuators. This is our evolution brochure, which outlines the components on the left all the way up to complete systems on the right-hand side. You can see some of our core product lines in here, including the Dual V guide wheels and components, and then Utilitrack linear guides more towards the middle, which are sub-assemblies, and then moving more towards the right are Low-Pro linear actuators. We are also the North American distributor of Hepco Motion automation products. And Hepco Motion, it has unique solutions including ring sections and curve sections. Just like our other products, they are available in components, sub-assemblies, and then complete driven systems. These can be used for very high frequency, high speed, high production applications. We provide products and services to many different industries and applications, so you might see some overlap into your specific industry. Many of our products are used in packaging machinery, in corrugate handling machines, as well as in paper and pulp production machinery. Our products also satisfy some higher accuracy requirements in testing and inspection, laser marking, and also in welding and pipe processing. So you can see that there's a very wide range of usages for our automation products. With a lot of good introductory content on the webinar, we're going to jump straight into the terminology and jargon. The term actuator was used in the title of this webinar, and it's essentially a mechanical device for moving or controlling a system. They have an alias or AKA. They can also be called a stage, a thruster, or a positioner. A linear actuator is a device that creates motion along one axis or along a line. A rotary actuator is a device that creates motion around a circular axis of rotation. You can see some examples of actuators on the bottom of this slide. the slick stick actuator on the left, Eco 60 in the middle, and a rotary HDRT solution on the right-hand side. So as mentioned on the previous slide, an actuator is a mechanical device. It's made up of several other component types, including primarily a linear guide and the drive mechanism, but it can also include other accessories such as sensors, limit switches, motor couplings, motor mounts, and gearboxes. Looking at the drive mechanisms, or power transmission, power transmission is the movement of energy from its place of generation, such as at a motor, to a location where the useful work is performed. The drive mechanism is the mechanical parts that convert the motor power into motion. Here are some of the most common types, including belts, chains, ball screws, lead screws, rack and pinions, and linear motors. A motor converts electric energy into mechanical energy and is the component that allows an actuator to be driven by a computer program. A coupler is also an important machine element that connects the motor to the actuator. There are several different types. Shown here is a flexible coupler, which is one of the most common. A few more terms that are relevant are listed here. A bearing is a machine element that reduces friction between moving parts. Friction is the force resisting the relative motion of solid surfaces. There's the coefficient of friction, which is a value that shows the relationship between the force of friction of two objects and the normal force between the objects. We typically use the coefficient of friction for a linear guide to show how efficient it is in moving and reducing friction. Backlash is any play or loose motion between two contacting parts. Backlash is important when evaluating a drive mechanism that may result in positional error on an actuator. And preload. Preload is an applied load which removes any clearance or backlash in mating parts. In many of these actuator designs, there's a mechanism for adjusting the preload of the linear bearing out of the system so that it reduces backlash and any play. When discussing the performance of actuators, these three terms are widely used: position, accuracy, and repeatability. The position is the spatial location of the carriage or moving component of the actuator. It's the physical location of the adjustable element. The accuracy is the amount of error expected when positioning to a location. Someone might ask, how accurately will that position? That means, how close to the target position is that capable of reaching? Repeatability is the amount of error expected when moving from and back to a location. And it can be thought of as how accurately does that repeat to that location. We use some other terms when describing our actuators. In the image below, you see a belt-driven low-pro, which is a low-profile actuator that we manufacture. We use the term drive end on the end of the actuator where the drive motor or gearbox is attached. This would be the left-hand side of this image. We use the term idler end when we discuss the opposite edge of the actuator. This is the end where the drive mechanism is supported. You can see here an idler pulley and tensioner for taking tension out of the belt system. We use the word wheel plate or carriage to describe the movable platform. It's a subassembly of linear guide bearings and accessories that you can attach machine elements or other devices to and then have those be the movable object. And since we're going over terminology and jargon, it's important to remember that there's a lot of regional variation. There is worldwide production on these type of products, but some of the most key players in this industry come out of the United States, the United Kingdom, Germany, Italy, Japan, Korea, and China. So some of these terms have synonyms that you might see being used by other companies or other manufacturers. So in general, a guide could be called a guideway, a rail, a slide, a track, or even a profile. A guide bearing could be called a wheel or a roller. The wheel plate is often called a carriage, a slider, or even a bearing block. A linear actuator could be called a positioner or even a single-axis robot. And when you attach multiple actuators together, it can be called a gantry system, a multi-axis gantry, or a Cartesian robot. So now that we have a baseline understanding of some of the terminology, we're going to take a look at the different guide types and drive types, also referred to as their technologies. In the rolling elements, we'll take a look at guide wheels, square rails, and ball bushings. We'll also look at sliding elements, which are low friction bushings, and they can also be special coatings on materials as well. We'll take a look at non-contact, air levitated, or magnetically levitated bearings. In the drive types, we'll take a look at the drives listed here, including undriven manual power. So the first guide type is a rolling element. The most common rolling element is with a ball bearing, and these can be with guide wheels or studded guide wheels. And these are used in linear guide tracks, as you can see on the right-hand side where the bearing itself is essentially a wheel or a roller, and it rolls on a linear track. This provides guidance in a line. The first guide type is guide wheel, which was invented and refined by Bishop Wisecarver under dual V motion technology. It has 90-degree precision ground running surfaces on the outside and double row angular contact ball bearings on the inside. It runs on a mating 90-degree track, which is made from hardened steel or stainless steel. It's a self-cleaning design that's ideal for harsh conditions such as heavy debris. It can be high-speed capable, up to 5.5 meters per second, and high accelerations up to 5 Gs. It provides smooth, quiet, low-friction motion, and it can be used for very long-length applications. It also provides moderate levels of accuracy. There are a few disadvantages to this technology, including the fact that it's a larger size versus load capacity. There's also a little bit lower accuracy than available in square rail technology. And the process of adjustment and taking out the preload can be somewhat confusing to new users. It also has moderate rigidity and stiffness, where other solutions may have improvements in these factors. The next type of linear guide is the square rail. It's also called profile rail or ball rail. These are very popular because they can be cost-effective and they work in a wide range of applications. They have some main advantages, including the 4-row angular contact to the rail provides very good stiffness. So they have very high load capacity versus the relative size of the carriage. They can be high speed as well, up to about 4 meters per second. They provide very low friction motion, and they're also capable of very high accuracies when they're ordered in the high precision grades. The square rails have some disadvantages too. There is some noise generated when the balls contact each other. They also require precision mounting surfaces, and that can add additional labor and time to install properly. They're relatively short travel lengths, and it can be difficult to combine several rails together because the balls are very small. Any joint or gap in the track makes a very big difference. Contaminants may jam the ball races and cause failure of the external seals. And the balls may fall out of the block when removed from the rail on some designs. Moving on to the next guide type is similar to the square rail. This one is the round rail. It's also called a ball bushing or round shaft technology. The advantages here is that they have a high load capacity versus its size, and they have many balls in contact, so it can spread that load out evenly. They can be very high speed as well, 4 meters per second, and provide low friction motion because of the ball bearings. They're capable of moderate accuracies, and they're medium to very low cost. And of course, some disadvantages. They have relatively low speeds when compared to the other technologies, the guide wheel and the profile rail. They can be difficult to mount to flat surfaces because of their geometries, and they require a base or they must run unsupported. Like in the example to the right-hand side, the steady rail is an unsupported rail. They generate noise due to ball contact inside, and contaminants that get past the seals can jam the ball cage and cause failure of the seal. Balls may fall out of the block when removed from the rail in some designs. Moving away from the ball bearing based guide types, let's take a look at the sliding element bearings. These you can see here are typically round and run on round shafting, and they have no moving parts. Some of the advantages: they have a very simple sliding design, and they're very debris tolerant, as you can see in the image there. They have good load carrying capacity versus the size, and they can be high speed. They provide very low friction motion as well, even though it's a little bit higher than a ball-based technology. They provide medium accuracies at the lowest possible cost. Some of the materials that is used is PTFE, which is widely known as Teflon, and UHMW. There's also proprietary polymers and other porous metals. The sliding element bearings have a few disadvantages. They can bind more easily than ball technology. They also have higher stiction or stick slip. This is a high initial resistance to begin moving. A moving sliding element bearing is very, fluid and smooth in motion, but sometimes it takes a high initial force in order to get it started. It also has faster wear characteristics as the sliding element wears out. It can be difficult to mount on flat surfaces because it's typically on a round shaft. And it requires multiple blocks to prevent rotation. So a round rod and with a round sliding element needs to have some anti-rotation included in the design. The last type of guide that we'll look at is non-contact. These are fairly exotic in nature. They can be either air levitated or magnetically levitated. So think of a maglev train as a big case example. There is no sliding friction, which is a big advantage because there's non-contact between the bearing ways. They can have very consistent velocities. They're also capable of very high accuracy, high repeatability, and high velocity. However, the amazing performance characteristics of non-contact guides come at some additional cost and peril. There are several disadvantages, including the high cost. There is lower stiffness than in contact elements. If this linear guide is floating within a magnetic field, it's not as rigid and stiff. It will have some compliance. It's also susceptible to vibration, and it requires complex motion control electronics, which aren't very efficient and generate a lot of heat. So we can compare and evaluate the different guide technologies to each other in a chart like this. You can see that a red box with a 1 is essentially the worst, and a blue box of 5 is the best. Since we just talked about rigidity and magnetic levitation, you can see that it's acceptable with a 3, whereas a square rail, a profile ball bearing, is 5. It's the best rigidity. Also on cost, you see we have some of the lower cost solutions, including the Teflon bushing is the best, and square rail costs a little bit more, and so does round rail, and so that's down in poor. It's a higher cost is worse in that case. So you can see here if you compare something like noise, guide wheels are very quiet. Teflon bushings and magnetic levitation is also very quiet, but the round rail and the square rail has a bit more noise and is a less advantageous there. So just keep this in mind if you wanted to compare essentially bearing to bearing or guide to guide. Okay, so now we're going to take a look at the other part of the actuator, which is the drive types and technologies. Even though an actuator typically will include a drive mechanism, let's take a look at undriven manual power as a comparison. We're going to take a look at belts, chains, lead screws, and ball screws. We're also going to look at rack and pinions and linear motors. I noticed an error on the slide in the top right corner. It says pneumatics. Pneumatics can be used as a drive type, but today we're going to look at linear motors in its place. Okay, so the first drive type, undriven or manual power. Some of the advantage of this, it's the lowest cost. If the person is the one moving it, it doesn't take a component or a product that you buy. It'd be done by hand. It also can meet the basic requirements of an application. And there's no lead time. You don't have to wait for those parts to arrive. However, on the disadvantages, it has very limited load to force capacity. It's required, the strength of the individual is the limit there. And it's very poor accuracy. Although we like to think that we can move perfectly, many cases we don't. And it's also very inefficient. You'll break a sweat quickly if you're trying to push a car. One of the most common drive types is belt. It's also called a tooth belt or drive belt. Some of the advantages here, they can run at very high speeds over very long travel lengths, and they're very commonly available for very short lead times. They require low maintenance, and they're very cost-effective. They come in a variety of various standard tooth sizes and pitches, and they can be used primarily in the horizontal orientation. You can see here the example is a steel reinforced polyurethane belt with an internal tooth profile. On the disadvantages side for belts, they provide moderate linear accuracy. You can see the case example of our Low-Pro on the right-hand side can have accuracies of about 0.08 of an inch per foot. They also have belt stretch and maintenance, so your design requires a tensioner or to remove some of the belt by cutting off some of the teeth. There's also the problem of wear and abrasion of those polymer teeth in dirty environments or just as life wears on. It also has a lower tensile strength when you compare it to some of the other technologies like a chain, which is made out of solid steel. And speaking of chain, here is this drive type. In this case, a roller chain with chain sprockets. Some of the advantages you see here, the highest reliability in dirty environments. Those big holes and gaps in the chain is a great place for dirt and debris to get pushed right through and out the backside. These can be used for very long travel lengths, and they're pretty common as well for short lead times. They have a pretty easy maintenance. They simply need a little bit of relubrication and cleaning occasionally. And they're a cost-effective solution. They have a very high tensile strength because they're made out of steel, and they're widely available in various standard sizes. These can be used in horizontal or vertical lifting applications. And of course, they come with some disadvantages. They result in a little bit lower overall speed and lower linear accuracy. In our case example on the right-hand side, you see an accuracy of about 0.15 of an inch per foot. This is due to the backlash in each link of that chain. There's a large amount of backlash over long distances. And these will also result in chain stretch maintenance, and you need a tensioner just like in a belt as those machine parts wear. And now moving on to the next drive type is lead screw. You can see on the image on the right it typically has a polymer nut on a screw helix, which can be very long and also pretty accurate. Some of the main advantages, high linear accuracy, and it can be non-backdriving, meaning in a vertical application or with a lot of force, it can not turn or rotate. And they're also available at a moderate cost. These can be used for vertical or horizontal applications. So screw drives are great, but there are some disadvantages. You're limited on the speed, and so the overall speeds are lower. There's also travel length restrictions based upon the screw stock availability and the sag over distance, which is due to a diameter and the length. They can have relatively long lead times as far as ordering or production, and they need to operate in relatively clean environments, so they must be protected if it's a very dirty application. And they also require a moderate amount of maintenance, primarily in cleaning. You can see an example on the right-hand side of a Low-Pro actuator, and its accuracy specification of 0.6 of an inch per inch, which is very accurate. Another type of screw is a ball screw. Instead of having a polymer nut, it actually uses tiny ball bearings inside a nut that has a ball return tube. It's a very efficient rolling mechanism similar to the guide wheel technology. The screw principle is about the same. It has a long linear helix. So some of the accuracies, some of the advantages here, it can be very high linear accuracy. These are main components used in precision CNC machines and other applications. But they do come in various precision grades. And so they can also have very high mechanical efficiency due to the ball rolling. And then they can generate very high thrusting loads. They can be used in vertical or horizontal applications. In vertical applications, however, there is the possibility of backdriving, and so a brake or other mechanical lock is recommended. As I mentioned on the previous slide, one of the disadvantages of a ball screw is that it can be backdrivable due to its high efficiency. It can also provide low to moderate speed. They're not generally thought of as high speed capable. And they can have travel length restrictions based upon their sag over distance. They're also limited on speed and length on the screw's critical speed, another factor that we will look at in our engineering roundtable. They also have a little bit higher cost and longer lead times to produce, and they have some high maintenance requirements. They must be kept clean and operate in clean environments. You can see the Low-Pro linear actuator example can generate about 4/1000 of an inch per inch in accuracy. This is because this product uses a rolled ball screw instead of a precision ground ball screw as far as a cost versus performance trade-off. The next drive type is a gear rack, or more commonly referred to as a rack and pinion. Some of the advantages here is it can have medium to high linear accuracy because they're available in various precision grades. They can have a low cost as cast version for cast racks, all the way up to a high cost precision ground gear rack, which is made to very high accuracies. And with the gear rack, you can have extremely long travel lengths because the racks can be made with tooth profiles to attach end to end for very long lengths. They can be used in horizontal or vertical applications. Looking at some of the disadvantages of rack and pinions, they must be used in low to medium speeds. They cannot attain the speeds of belts or chains. And they also generate some noise during operation, so it can add a bit more sound into a factory environment. They're also relatively high cost and must work in clean environments and applications. Lubrication is really critical on a gear rack because the teeth, as they mesh, directly rub and wear on each other. And so there is a moderate maintenance requirement. The last drive type that we'll look at today is a linear motor. Its construction is very similar to a rotary motor, except that it's in a straight line. It uses fixed magnets and a coil assembly, which is energized, causing linear motion. Some of the advantages, the output is directly force instead of torque, which must be converted. So it's a linear, not a rotary to linear mechanism. The force is applied with no intermediary, such as a belt, lead screw, or a pulley. It's ideal for linear motion. It's pretty much pure motion in one direction. And there's also no friction in the drive mechanism. It's very high accuracy and repeatability capable, and it can also be very high speed. These can be used in any orientation from horizontal or vertical. So the incredible accuracy and performance of a linear motor comes with a few downsides, one of them being that they must be precisely guided. You must keep the coil in the center of the magnetic field for the maximum force transmission. They're also pretty expensive. They have an inefficient use of energy, and so the controllers generate a lot of heat during use. There is also the potential of having moving cables and umbilical cords, so those need to be figured out in the design. They also require linear encoders for position feedback. On a motor with a pulley or a chain sprocket, a rotary encoder is possible, and these are typically of lower cost. Looking at the right-hand side, you can see an application from Hepco Motion on the Beckhoff extended track system. It's important to note that a linear motor can also be manufactured around a curve for circular or oval transmission. So just as we did with the linear guide types, let's look at a chart of comparisons between the different drive types. You can see here on a scale of 1 to 5, 1 being worst and 5 being the best, that undriven is undeniably the worst application. It's the lowest speeds, lowest accuracies, probably generates a fair amount of noise, and is difficult over long lengths. But the only benefit of that is that it is the least cost. You can see some of the major advantages of linear motors that we just discussed, namely that it can be very high speed, very high accuracy, but it does not work as well in dirty environments, and it's also of a higher cost. So you can see here a variety of different choices and how they relate to each other. It's not a hard, fast rule, but it is somewhat of a summary to compare one technology to another technology. When considering and selecting an actuator system, one of the other key components to think about is the flexible shaft coupling that is used to connect the drive motor to the actuator shaft. Here are some of the key elements to think about early on in the design so that you're not faced with a situation where a standard coupling can't be used. You should plan to use a flexible coupling because there was always some amount of misalignment. A solid, non-flexible coupling will cause excessive bearing loads and premature failure. Consider the physical size, such as the outer diameter of the coupling, overall length needed to connect the shafts, and of course, the shaft diameters being connected. Misalignment from the machining and tolerances of mating parts will determine the amount of misalignment that the coupler must accommodate. Don't forget that there is angular, parallel, and axial motion involved. Torque must be evaluated during operation and during peak conditions, such as startup or rapid stopping. Torsional stiffness of the coupler will directly affect the position accuracy of the linear actuator. Attachment methods vary, but the clamping design is usually preferred for linear stages because of the positive engagement and easy installation or removal. This chart provides a brief summary of the variety of coupling types and their abilities to provide a solution in several categories, including the amount of misalignment they can compensate for, their torsional stiffness, and their backlash. This is a guideline, so if you have any questions, it's important to talk to our application engineers or with an engineer at the coupling manufacturer. Many companies will provide prototypes for testing in OEM applications. So now that we looked at the different guide types and drive types and coupling types, you'll have an understanding when you compare what the content is of an actuator, and you can look at their intended purposes from a design to another design. You can see here our signature motion linear actuators, our Lopro actuators, and our HEPCO motion actuators. Just as a rough guide over here, we take a look at the Eco 60, the first one. It has sliding elements with a lead screw drive. It's meant for lower load capacities and for fairly high accuracy, high speed positioning with the lead screw over short or relatively short distances. Our slick stick and our twin light also have sliding elements and lead screw drives. The MP series, however, has an SR in the box. It has square rail guides with a ball screw drive. These can be higher positional accuracies, higher loads, and a more rigid moment load capability. Steady rail, RR, has round rail with a ball screw. The round rail is a low-cost solution, and it can be used in many different environments, but is likely unsupported across its span. XLA 9s and XLA 15s have square rail with ball screw drives. These are very rigid, high-thrusting actuators, and you can see those in the lower left-hand images. Our Lopro has guide wheel linear guides and a variety of different drive types, many different types, including belt chain, lead screw, and ball screw. You can get these also in an undriven version. Looking at Hepco Motion adds in the gear rack as a drive type. So you can see that based on your application and your understanding of these different technologies, it might lead you in the direction of deciding whether that actuator is going to work for your application. I think of it as a coarse screening or a filtering, as you will. So here's another interesting graphic which might help to outline the different actuators compared to each other. On the bottom axis, it's not very scientific. We just have good, better, and best. It's easy to assume what this might include. Best would be highest accuracy, maybe the highest precision, most durable, highest moment load or thrusting capabilities. On the vertical axis, we have the money on the dollar signs, the lowest cost up to the highest cost. And as you would imagine, a simply good actuator might have the lowest cost. So you can see the sliding element actuators at the bottom down there, the Slick Stick, Eco 60, and Twin Light. And also moving up towards the better in the middle range between better and best is the Low Pro actuator, which is a bit more expensive on the scale for the dollars, but not all the way to the top. And then when you look at our most accurate, highest positioning, most load capacity, the XLA system, you can see that its performance also comes with the price tag as well. So it's likely that you'll find an actuator somewhere within this range for your application. Remember that your application requirements will mostly be what dictates the type of guide and drive type that you can use or that will satisfy your requirements. So although it is possible to self-select your own actuator and specify your requirements, we like to help our customers, and you can see here our application data sheet. If you can have the documented requirements and parameters of what you're trying to do, we can help to select an appropriate actuator and also do some supporting calculations. The more information that you provide on this form, the better off our application engineers are in making an appropriate selection. Of course, we need to know the forces, both static and dynamic. The speeds that you're likely to be using, as well as the accelerations, will help us determine a motion profile or a motion curve. We also need to know the duty cycle and the environmental conditions. Of course, the orientation is important so that we can calculate moment loads and other loadings. The life expectancy that you require for your application is very important and also relates to sizing. Typically, a larger bearing can last a lot longer given an equal amount of load. Also, your budget and cost considerations and lead time requirements are very important. Different products like a ball screw might take a little longer to produce than a belt drive actuator. And so if you're in quite a hurry or time crunch, it might be beneficial to select an actuator that's more easily made. So we have this form is available also on our website. You can go to bwc.com/request-quote in order to fill this out electronically.
Okay, so this brings us to the engineering roundtable, and we're joined today with our application engineering department. Today we're going to talk about best practices for selecting actuators, and then also go over some advice and other considerations. So let's do a quick introduction and overview of how long you've been with Bishop Weiskarber.
Hi, my name is Ariel Oriel. Been with the company for about 16 years.
Dan Fletcher, mechanical engineer. I've been here for 19 years.
Ben D'Amico, applications engineer. Been with the company for 6 years.
Chris Bullock, also applications engineer. I've been here for a year and a day.
Wonderful. All right, let's take a look at some of the first questions that we have here, things that would be good to ask an engineer. So Ariel, can you tell us about the factors that you consider during actuator selection?
The main factors I usually consider would be the payload weight, the speeds, accuracies of positioning the particular payload, and other secondary factors such as environmental conditions, temperatures, how dirty the environment is, orientation of the actuator itself. Those are pretty much the primary and fairly important things I would consider first. So,
when you look at an application data sheet that's submitted by a customer, what stands out at you as a red flag or an area of concern?
Usually speed, environment, conditions a lot of times. Those would be a few factors. Accuracy sometimes, which is one of the first things we'll look at. Ball screws are typically the most accurate system we're going to sell. If we're looking for fast speeds, we'll trend towards belt drives, long lengths, belt drives, chain drives, rack drive. Most of the limitations on screw driven are by the length and the diameter of screws we can fit into the systems we have. Those are the main things we look at. But then one of the other things is the actual size of the mass that you're moving and its center of location with respect to the carriage.
So essentially the load capacity of the carriage itself on the actuator, whether it's appropriate for the task.
Right. If you got moment load you're dealing with, if the mass is extremely large compared to the size of the carriages we offer, we can throw on secondary carriages on actuators, or we can pair up actuators in parallel, put multiple carriages on there to support larger loads.
Great. Okay, for the next question, can you explain how the critical speed of a screw drive comes into play for an application? How about Ben?
Sure. So the critical speed of a screw drive depends on the length and diameter of the screw. So up to a certain point, if you have let's say a thin screw and a really long length, you're going to experience a lot of whip. A thicker diameter screw at the same length, the critical speed there will be a lot larger versus a thinner screw, basically due to whipping action.
So why would the critical speed be an issue for an application?
Sometimes, we can't meet a customer's spec. Sometimes a screw is required for the needed thrust force of the application, but it doesn't quite meet the speed. So that's usually the pickle we find ourselves in. So
in some applications, is screw whip a problem, or does that cause vibration, or what does the screw whip when you're above the critical speed do?
Yeah, so basically it causes vibration. The screw is basically whipping, and so it's a recipe for disaster.
Okay, on the next question we have, tell us a little more about back driving of a screw, perhaps in a vertical application. Chris, do you have any input as far as back driving?
Yeah. Basically, if the screw pitch is too large, you can just manually push the carriage and it'll slide along and back drive that screw. This is particularly problematic when you are in a vertical application because the weight of the payload or even the carriage itself can be enough to just make the whole thing fall, especially with screw types like ball screws that have very low friction. Usually in vertical applications, if you have a ball screw or a lead screw with a high pitch, we recommend equipping an electric brake to it in order to hold it still to prevent back driving.
Okay, great. So to Ariel on the next question, can you tell us a little more about how you size an actuator for an application and perhaps about some of the equations that we use?
All right. Well, the first factor that I look into is the payload weight. How much weight are we asked to move? Secondarily, we look at the speeds with which the payload needs to move. And thirdly would be the length of the actuator. Now, in terms of the equations we use, mainly it is the static and some dynamic equations that we would use. I guess the main one we always use is F equals ma. We also consider what forces acceleration will impart on the actuator and whatnot. And we need to compare those forces to the capacity or the capability of a particular actuator. Therefore, that will help us determine the size of a particular drive or actuator for an application.
And then after that size, do you do any calculations on estimated life?
If the customer asks us to do this, yes. We can estimate bearing life. Now, please keep in mind, The bearing life is just the life of the wheel or the ball bearing life, that if you're using a guide wheel type technology. It does not give us an estimate on life with regards to the other components, such as the track or the drive mechanism itself, the belt, chain, or whatnot. It does give us just an idea of how much life we can expect from the wheels themselves, given a particular conditions of the application.
Okay, great. Couple more questions, open up for anybody. What accessories are available to make a more complete motion system?
On a lot of our actuators, we offer limit switches. We offer adapters to couple customers' gearboxes or motors. We also offer gearboxes, motors, stepper, servo, AC. We offer line shafts for putting two belt-driven or chain-driven systems in parallel.
Gantry brackets
Gantry brackets to attach the actuators together in configurations. We do take the systems that we offer with motors. We can offer drivers and controllers and get as much as turnkey packages for customers that are interested.
Excellent. Okay, so in your daily work, do you see common mistakes that new customers or other inexperienced engineers might make when selecting an actuator?
I personally like customers that fill out the application data sheet and don't choose the product. They allow us to choose it, and then we can steer them in the right direction. You'll get some engineers that will actually look at brochures and say, hey, quote me one of these. And then you'll get application details and find out that what they're looking for doesn't work. So that's how I prefer to take on applications is don't tell me what you think you want, just tell me what you're doing.
Also, some customers, when they see the word stainless steel, they automatically assume it's corrosion proof, which is not the case for the stainless steel that we use. We use the 400 series primarily, so all that is corrosion resistant, but it's not a full weatherproof material.
The reason we choose that material is because of the hardenability of that material in order to function properly in a guide wheel rolling friction mechanism.
Great. And then the last question that we have today is, what is your best advice for someone looking to use an actuator for their motion control project?
Give us as much information about the application that you're doing and let us help you make the right choice.
I would also recommend, before you even start to choose an actuator, make sure you really nail down exactly what it is you're looking for and what you need it to do. Things like payload, speeds, acceleration. If you don't have that for us, it makes it difficult. But on the other hand, it's very likely that you'll end up purchasing something and then it won't be able to perform for what you end up needing it for. So sometimes that extra 30 seconds to double check your technical requirements can save you a lot of time and hassle.
Any other recommendations?
If you can provide a sketch of the application of your setup, that will give us a visual representation and give us a better idea of what you're trying to do.
How about being prepared for changes and back and forth?
Oh yeah, just multiple iterations, going back and forth, a lot of communication with us here and with you as a customer, just to make sure we get the system right. Understanding the duty cycle, how long, how often it's going to be basically running and how long you expect it to run. And just understanding the basic motion profile, is it going to do a lot of start-stop, continuous motion, any significant acceleration, all of that. So just describing as best as possible the motion profile will help tremendously.
Great. Okay, thank you very much to our engineering roundtable.
Hi, everybody. It's Mike Santora. I'm back. I apologize for a little technical snafu there. So I want to get down to the next question for Brian here. So what are some of the maximum thrusting loads your actuators are capable of, Brian?
I don't have that value on the top of my head. We'd have to look that one up and see. But in general, it would be for a ball screw unit with a profile rail guide. And so our XLA system would have the largest thrusting capacity. You'd also want to look for the largest ball screw diameter. That will also provide the most power in that direction used as a thruster.
And Brian, I apologize if this is the question that Stacy answered while I was on, but we have one here for pneumatic servo actuators. Are you seeing a trend in the industry to use these type of actuators? Advantages, disadvantages there?
Yeah, we're not seeing very many requests, if any, on pneumatic servo actuators. In general, we don't do a lot of field a lot of requests for pneumatics. Sometimes we use pneumatics on accessories, but not as a primary drive type. Perhaps this is a new technology that's taking off, and so we'll see some developments of that in the future. But as of yet, we haven't fielded any customer requests for that technology.
Okay, we have another question coming in. It says, do you have a process to optimize a ball screw for diameter versus pitch to get the best combination?
Oh yeah, we can evaluate different ball screw diameters, and we look closely at what's called the critical speed. And each ball screw has a characteristic of its critical speed. That's essentially the maximum RPM versus the length, and that vibration is typically known because the screw material and the screw physical properties are known. And so a screw from a manufacturer is provided a critical speed. And so we can evaluate the different critical speeds for different ball screws for an application.
Okay, Brian. Well, I think we are just about out of time. I want to thank everybody for attending the webinar and, of course, sticking around while my telephone went through a catastrophic failure. I do appreciate it. Just another reminder that, of course, this will be emailed to everybody later today, and it will also be available at www.designworldonline.com. And thank you for listening.